In this video, we're going to solve another LP practice question, question number 15 from chapter 11, which is about product mix optimization. So here I have the question for the Bay Oil Company. We want to find the product mix, the best mix of product. So they are offering two types of products to the market, two types of fuel, regular and super. And in order to make each one of those, they mix three types of ingredients. So for each ingredient, we have the cost per barrel, we have the octane level of each ingredient, and we know exactly how many barrels of each ingredient they have available in their inventory. Also, for each type of fuel that they're going to sell in the market, we know exactly how much revenue they can make. And we also know the demand. We also know the maximum demand. So they want to find the best mix, the mix of products, the best way that they can mix ingredients in order to make their final product. And their objective function is the profit that they make. And the profit would be revenue minus cost of ingredients, all right? And there's only one thing, one consideration that is very important. And the octane level is the one that defines the type of fuel. For the regular fuel, they have to have a minimum octane level of 90. And for super, they have to have at least an octane level of 100 units. All right. So this is the octane level constraints that they have to be, they have to really be careful of. And the way we actually find the octane level is by finding the weighted average of octane level of the ingredients for each type of fuel. All right. So let's get it started. So first of all, what are the decisions that we have to make? We need to understand, we need to find the best mix. So that means how much of each ingredient will be used toward producing each type of the fuel, each type of fuel, right? Each type of the final product. So the decision that they have to make is how much of ingredient I to be used for production of fuel type J. And I'm going to call this Xij. So Xij is the amount of I, the amount of ingredient I to be used for production of fuel type J. And J can be either R, regular, or I'm going to go with 1 and 2, R for regular and 2 for super. So that's the decision that they have to make. And objective function would be to maximize profit. Maximize profit, and profit would be the revenue that they make minus the cost of ingredients. So 18.5 is the dollar amount of revenue that they make per barrel of regular, type regular. But how much? Now 18.5 is the revenue that they make per barrel, but how many barrels are they making? So I said ingredient I, fuel type J. So fuel type J, so we're going to focus on J equal to 1 for regular, but then the total amount of production of regular is going to be equal to the amount of ingredient 1 plus the amount of ingredient 2 plus the amount of ingredient 3 that are used for production of regular regular fuel type. So X 1, 1 plus X 2, 1 plus X 3, 1. The amount of ingredient 1 that is used for production of regular, the amount of ingredient 2 used for production of regular type fuel, plus the amount of ingredient 3 used for production of regular. So that is the total amount of production of regular type, plus $20 would be the revenue per barrel of super type, super fuel, right? So X 1, 2 plus X 2, 2 plus X 3, 2. The amount of ingredient 1 used for production of fuel type 2 or super, the amount of ingredient 2, X22, the amount of ingredient 2 used for production of super, X32, the amount of ingredient 3 used for production of super type, super fuel, all right? So that's the total revenue. And we should now subtract the amount of the cost, the amount of ingredient cost, basically. And the ingredient cost, we need to we need to use these costs per barrels and multiply by the amount of usage of each ingredient. So it's going to be minus 16.5 times the amount of ingredient 1 used either for production of regular fuel or super fuel. So it's going to be X11 plus X12. All right, ingredient 1 can be used either for regular or super. Each barrel that you use is going to cost you 16.5 minus 14 times X21, X22. Minus 17.5 is the cost per barrel for ingredient 3. X31 plus X32. And that characterizes the objective function, the profit that we want to maximize, all right? Yeah, and then what I can do, actually, it's okay. I'm just gonna move on. So that's the objective function. And then the set of the constraints, we have subject to the list of constraints, and the constraints that we have the availability of each ingredient, and we also have demand. And also we have to make sure that we're respecting the octane level of each fuel type. So I'm just going to go with the supply and demand limitations that we have for the ingredients availability. So for ingredients 1, 2, and 3, ingredient 1, let me just put it here, ingredient 1, 2, and 3. So for each one of them, the total amount used of each ingredient should be less than or equal to the maximum available amount. So for ingredients 1, the total amount used is X11 plus X12. And this should be less than or equal to 110,000 barrels. X21 plus X22 should be less than or equal to 350,000. X31 plus X32 should be less than or equal to 300,000. All right, so the ingredients availability, this should be linear, and we have the total amount of ingredients used should be less than or equal to the maximum available amount of each ingredient. All right, so this is the ingredient availability, and then we have the maximum demand constraints. So for fuel type 1 or regular, and then for super, which we called it type 2, we use index 2 for J equal to 2 for type super. And so for regular, the total amount of regular that is produced should be less than or equal to 350,000. All right, and this is the total amount, X11 plus X21 plus X31. This should be less than or equal to 350,000 X. And then the total amount of production of super, which is X12, X22, X32, the sum of these three should be less than or equal to 500,000. X12, X22 plus X32 should be less than or equal to 500,000. All right, so you won't be able to sell above these amounts, so you shouldn't produce above the maximum demand, right? And then you can't necessarily you can't violate the supply constraints. You don't have more than 110,000 barrels of ingredient 1, so you can't really use more than that for production. So this is what we're doing here. And then, like I said, we have two more constraints to consider. We have the minimum octane level of regular and super fuel types. So I'm just going to add that. Octane or minimum octane level. Minimum octane level for each fuel type. So we have to define this. For both types, regular and super. So for the regular, like I said, the weighted average of octane level should be weighted average of octane level of its ingredients should be greater than or equal to 90. All right, but how do we measure that? So we know that we're using X11 plus X21 plus X31 units of ingredient 1, ingredient 2, and ingredient 3. And then they have different octane level. All right. In order to find the octane level of the final product that is basically a mix of all these products, we need to find the weighted average. The way we find the weighted average is by multiplying the amount of production by the octane level of each ingredient type, and then divide the whole thing by the total amount, the total amount of production of, let's say, regular type. All right, so let me just write it down. So we have 100 is the octane level of ingredient 1. So for regular type, we're using X1 1 unit in that, plus 87 times X21 plus 110 X31. So that is this is But what I just did, I multiplied the octane level of each ingredient by the amount of usage of each ingredient in final product one, which is the regular type. If I divide this by the total amount of X11 plus X21 plus X31, that will give me the weighted average. All right. In other words, I'm multiplying by doing this. I'm multiplying 100 times x1 divided by x11 divided by x11 plus x21 plus x31, which is the weight of ingredient 1 in production of regular type, plus 87 times x21 divided by x11 plus x21 plus x31, which defines the weight of ingredient 1 in regular type product, plus x31 divided by x11 plus x21 plus x31 times 110, which is the octane level of ingredient 3. So basically, I'm multiplying the octane level, I'm multiplying the weight of each ingredient in the regular type product by their octane level. And that should be greater than or equal to 90 for regular type. And I should have the same thing defined for super type, except that it's going to be the second index. It's going to be always 2. So x1, 2, x2, 2, x3, 2 should be greater than or equal to 100. 100 is for the minimum octane requirement for super fuel type. All right. Everything looks almost ready. And then we have the non-negativity. Which simply says xij, all xij should be greater than or equal to 0. You can't, you can't, the amount that you use from each ingredient toward production of each fuel type cannot be negative. I mean, it can be 0, but it can't be negative. So everything looks good except one thing. You won't be able to solve this using solver. The problem is, I want you to pause and think about this. What is the problem with this formulation? There's a problem that it looks actually minor, but it's indeed a major problem. It doesn't allow you to use Excel solver, or at least simplex method to use and solve these problems. The problem with this formulation is that this minimum octane level constraints, they're not linearly defined. This, the left-hand side, as you can see here, this is not a linear function. All right, this is a fractional, proportional function. This is a ratio, and in both numerator and denominator, we have unknown. We have decision variables, which makes it non-linear. It's not linear anymore. So what we need to do before we go ahead and put this into Excel solver, we need to first convert this into linear form functions, and then we can go ahead and put it in Excel solver. So what I'm going to do, I'm going to just copy this. I'm just going to cut this, move it down, and right below this, I'm going to go ahead and write down the converted version. So how do we convert this to linear form? Think about that. If we multiply both sides of this inequality by the denominator of these ratio by x11 plus x21 plus x31, as long as this is not 0, and as long as this is positive, we can simply keep the signs and we can just move on. We can convert it to the linear format and move on. So what I'm gonna do, I'm gonna multiply both sides of this inequality by x11 plus x21 plus x31. And let's see what happens. So if I multiply that by the denominator here, it's gonna what I'm claiming here is that this is equivalent to this one. And I didn't do anything except multiplying both sides by x11 plus x21 plus x31. If you multiply 90 by that, this is it. This is your new right-hand side. If you multiply the left-hand side by the denominator, it's gonna just go away, right? So you can cancel out and you will have only this part of your fraction. And now we have a linear function. So this is actually the linear equivalent of the first constraint. And I'm gonna do exactly the same thing for super type. So if I just copy this, paste it here. So that's all we needed to do in order to make this formulation linear. So now I can go ahead and solve these problem. So what I'm gonna do, so we're done with the formulation now. We now have a linear formulation or formulation of a linear programming question. So let's go ahead and solve this. But before, I'm gonna write down the list of parameters that I have here. So I have for ingredients, 1, 2, and 3. We have cost per barrel, 16.5, 14, 17.5. We have octane level, 187, 110. And we have the availability. We have 110,000, 350,000, and 300,000. All right, and then for each fuel type, we have the revenue and we have the maximum demand. And I'm gonna write down the fuel types into different, instead of writing them into different rows, I'm gonna write them into different columns because I'm gonna have my ingredients in different rows and my fuel types in different columns. That'll make it easier, and I'm gonna be able to use some product function. So the revenue or price per barrel would be 18.5 and 20, and then max demand would be 350,000, 500,000. All right, so this is the list of parameters. Now I'm gonna go ahead and develop my spreadsheet model. So decision variables are gonna be the mix of each ingredient within the production of the final product. So I'm gonna go ahead and have 3 ingredients and 2 fuel type. All right, so these 6 are my decision variables. The amount of ingredient 1 used for production of regular type fuel, ingredient 2 in regular, ingredient 3 for regular type fuel, and then same thing for super, all right? So that's for my decision variables, 6 decision variables. Objective function is the profit that we want to maximize. I just write it down, maybe here, objective, which is profit. And it's going to be simply, let me just put it right here. It's going to be the profit that we make out of, sales of these fuel types minus the ingredients cost. So I'm going to be, before I write down my objective function, let me just do something else, because I need to multiply the sum of the 3, and that would give me the total production of regular type by 18.5, all right? But before that, I'm just gonna write down this, so it would be the total production of regular and then total production of super. That way we don't have to write it every time that we need it. Just write it one time, put it in a cell, and then we're good to use it every time. So total production of regular is the sum of the 3. Total production of super fuel is going to be sum of the 3. And also, let me just move this one also to here. And then also, so that was the total production. Here is the total ingredients used, basically. Total used. It would be sum of these 2. Total amount of ingredient 1 used for production, total amount of ingredient 2 and ingredient 3. And the formula will be simply sum of these corresponding 2 cells, all right? So now I can, that would make it easier for me to write down the objective function. I can go ahead and write down the profit for, write down the revenue first. So it's going to be sum product of 18.5 and 20 by the total production of regular and super. I'm following exactly what I've already written here. 18.5 times the total production of regular plus 20 times the total production of super minus sum product of the total amount of each ingredient used multiplied by cost per barrel of each ingredient. So that would be my objective function, the total profit all right. Objective function. Now we can move on to, let me highlight this. Now we can go ahead and write down the constraints. We have the ingredient availability constraint, which can be defined right here. Let me actually do that. Let me just take this objective function from here, go a little down, put it right here, put it maybe even a little further down. So the total amount used, we had this constraint. The ingredient availability, the total amount used should be less than or equal to, this should be less than or equal to 110,000, 350,000, and 300,000 for each ingredient. So the total used should be less than or equal to the total available. All right, so that would defines my availability constraint. Maybe I just take this, maybe go up a little bit. All right, the total availability and also the maximum demand. This should, the total production of each type of fuel should be less than or equal to the total, the maximum demand available for that fuel type. All right, so I can just put this also into a different section, and I'm gonna, total production should be less than or equal to a maximum demand. Total amount of ingredients used should be less than or equal to the total amount available of each ingredient. So we just took care of these two sets of constraints. There are 5 constraints. We just did it. We just completed, right? And then we have to now write down these 2 constraints, the minimum octane level, and then we're good to go. We can just go ahead and put it in the solver. So let me just bring this up a little bit, the objective function, and I'm gonna write down the octane level right here, and we go from there. So the minimum octane level for fuel type. So here, when I'm writing it here, this is what it's going to go to the solver. I have to make sure to go with the linear form. So the minimum octane level, we need to define it for both regular and super. So for each one, I have a left-hand side, which is going to be this. The left-hand side is, if you look carefully, it's going to be the octane level, some product of the octane level, and the mix in regular. So that's the left-hand side here, and that should be greater than or equal to 90 times the total amount of production of regular. So I'm just, now that we know the constraints, I'm just gonna follow with what we have written here, what we have here, right? So it's gonna be, the left-hand side is gonna be some product of octane level and octane levels and the ingredients used for regular type fuel. And this should be less than or equal to, or sorry, greater than or equal to, it's the minimum level. So this should be less than or equal to 90 times the total production of the fuel type 1 or regular type, which would be this. And so that's great. So we just wrote the both left-hand side and the right-hand side for the regular type for the minimum octane level constraint. We just need to write it down for super type, right? For super fuel. Same thing, it's going to be some product of the octane levels of each ingredient multiplied by the amount of each ingredient used for production of super fuel. This should be greater than or equal to, this time 100 times, the total production of super fuel, x11, x12 plus x22 plus x32. Sum of those, the total production of super fuel, right? So now that'll take care of the right-hand side, all right? So I think we have everything that we needed to have. So we have the decision variables, the highlighted cells here, 6 of them. We have the availability of the ingredients. We have the demand for the final products. We have the objective function, and we have the minimum octane level for fuel type. We're going to add the non-negativity to the solver. So I think we're all set. We just go ahead, go to the data tab, solver, and we're gonna go ahead and maximize objective function, the profit, by changing only these 6 are my decision variables. So only all these highlighted cells subject to the supply constraint, subject to the demand constraint, and subject to the minimum octane level for each type. So we have the left-hand side for regular, greater than or equal to this cell, all right? And same thing for super fuel, RHS. So everything is good. All right, so supply, demand, and minimum octane level constraints, 2 of them. Make sure to change the solving method to simplex LP. Make sure that non-negativity constraints is checked. And all is good. So let's go ahead and solve this. So luckily, Excel found an optimal solution. There is a feasible optimal solution. Let's take a look at it. I don't need, for now, I don't need the answer and sensitivity to answer this question. It just asked for the optimal profit level. So this is really the schedule. This is how you can mix the product and get the maximum profit that is possible for this problem. So we're producing both products, super and regular. This is the total production of each one. We are, for super fuel, as you can see here, we are producing up to the maximum demand level. But for regular type, there is still some slack here. So we still have about exactly 90,000 barrels of regular to produce more. So the market still needs that. We have still room for that. But then since the profit of super was higher, we went all the way to the maximum demand that is in the market. So we produced exactly 500,000. For ingredients, as you can see, we used all of them. So all the ingredient constraints are binding, which was actually what we expected. So the octane level, now if you need to know the octane level, you need to divide the left-hand side. So the octane level, the actual octane level is this for the regular type, is the left-hand side divided by the total production of type 1. So let me just write it down. Octane level for regular is going to be the left-hand side divided by the total production of left-hand side. And for the super is going to be the left-hand side divided by the total production of super, which is 100. So you see both of them are a little higher than the minimum requirement, which is perfect.